Assalamualaikum and hello everyone. We are from Group 4 and we will be presenting Chapter 6, the second law of thermodynamics. I will be presenting the introduction of second law of thermodynamics. The second law of thermodynamics states that the state of entropy of the entire universe as a closed system will always increase over time. So, what is entropy? Entropy is a measure of randomness of the system or a chaos within a closed system. There are a few factors that cause an increase in entropy of the closed system. Firstly, in a closed system, while the mass remains constant, there is an exchange of heat within the surrounding. This change in the heat content creates a disturbance in the system, thereby increasing the entropy of the system. Next, thermal energy reservoir. Thermal energy reservoir are hypothetical bodies with a relatively large thermal energy capacity that can supply or absorb finite amount of heat without undergoing any change in temperature. This is also known as heat reservoirs since they supply or absorb energy in the form of heat. For example, large body of water such as ocean, lakes, river, or even atmospheric air can be modeled accurately as a thermal energy reservoir because of their large thermal energy storage capabilities or thermal mass. A reservoir that supplies energy in the form of heat is called as a source. Meanwhile, the one that absorbs energy in the form of heat is called a sink. Next, Group 4 representing the next subtopic is reversible and irreversible processes.
Now, let's move to two important processes in second law of thermodynamics. There are reversible process and irreversible process. What does it mean? Reversible process is a process that can be reversed without leaving any trace on surrounding. That is, where the both system and the surrounding are returned to their initial states at the end of the process of reverse process. This can be happen when the net heat and the net work exchange between the system and the surrounding is zero for combined process. Combined process is the combination of original process and a reverse process. Next, what is irreversible process? In irreversible process, the surrounding usually do some work on the system, therefore do not return to its original state. In real life, reversible process actually do not occur in nature. Mostly in nature, it involves irreversible process only. But the fact is, most of the engineers is interested in reversible process since it just consumes the least work. Just for addition, the reversible process lead to the definitions of the second law efficiency for actual process.
The factors that cause a process to be irreversible are called irreversibility. The first irreversibility is unrestrained expansion of a gas separated from a vacuum by a membrane in thermally insulated container. When the membrane is ruptured, gas rush into the empty side of the container, thereby expanding freely and fill the entire container. The gas would have to be compressed and heat transferred from the gas until its initial state is reached to restore the system. Since the work and heat transfer involve a change in surrounding, the surroundings are not restored to their initial state, indicating that the unrestrained expansion was the irreversible process. Hence, what is the second factor of irreversible?
The next factor is friction force. Friction force occurs on the interfacing surfaces of two bodies that move against each other. For example, a piston. When a piston is being pushed downward, some work is needed to overcome this friction force. The energy used as work becomes heat, causing the temperature rise at the interfacing surface. Reversing the direction of the piston's motion doesn't restore the original state. Instead, more of the work is converted to heat while overcoming the friction forces. This process is known as irreversible. The larger the friction forces involved, the more irreversible the process is. Friction isn't limited to solid surfaces. It can occur between fluid and a solid or between layers of moving fluid. So, what is the third factor?
What is heat transfer? A third form of irreversibility familiar to us all is heat transfer through a finite temperature difference. Consider a can of cold soda left in a warm room. Heat transferred from the warmer room air to the colder soda. The only way this process can be reversed and the soda restored to its original temperature is to provide refrigeration, which requires some work input. At the end of the reverse process, the soda will be restored to its initial state, but the surrounding will not be. The internal energy of the surroundings will increase by an amount equal in magnitude to the work supplied to the refrigerator. The restoration of the surroundings to its initial state can be done only by converting this excess internal energy completely to work, which is impossible to do without violating the second law. Since the system, not both the system and the surrounding, can restore to its initial condition, heat transfer to a finite temperature difference is an irreversible process. Heat transfer can occur only when there is a temperature difference between system and its surrounding. Therefore, it is physically impossible to have a reversible heat transfer process. The smaller the temperature difference between the bodies, the smaller the heat transfer rate will be. Any significant heat transfer through a small temperature difference requires a very large surface area and a very long time. Therefore, even though approaching reversible heat transfer is desirable from a thermodynamic point of view, it is impractical and not economically feasible.
There are three processes involved: internally, externally, and totally reversible process. A typical process involves interaction between a system and its surroundings, and reversible process involves no irreversibilities associated with either of them. A process is called internally reversible if no irreversibilities occur within the boundaries of the system during the process. During an internally reversible process, a system passes through a series of equilibrium states, and when the process is reversed, the system passes through exactly the same equilibrium states while returning to its initial state. That is, the paths of the forward and reverse processes coincide for an internally reversible process. The quasi-equilibrium process is an example of an internally reversible process. A process is called externally reversible if no irreversibilities occur outside the system boundaries during the process. Heat transfer between a reservoir and a system is an externally reversible process if the outer surface of the system is the temperature of the reservoir.
The third process is called totally reversible or simply reversible because it involves no irreversibilities within the system or its surrounding. A totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi-equilibrium changes, and no friction or other dissipative effect. So, let's see the example together. Consider the transfer of heat to two identical systems that are undergoing a constant pressure phase changes process. As we can see here, both processes are internally reversible since both take place isothermally and both pass through exactly the same equilibrium state. However, the first process shown is also externally reversible since heat transfer takes place through an infinitesimal temperature difference. Next, the second process is externally reversible also since it involves heat transfer through a finite temperature difference. So, anyone has any question to discuss together?
I have a confusion. How could we distinguish between internal and external irreversibilities?
Let me answer for this question. When the irreversibilities that occur within the system boundaries, then there are internal irreversibilities process, whereas when irreversibilities are process which occur outside the system boundaries, then there are external
irreversibility process.
Wait, I have a question. The situation is a cool candle is left in a warmer room where its temperature rises as a result of the heat transfer. Is this a reversible process? Can anyone explain to me?
Let me answer this question, JESNITA. I think the answer is no, because it involves heat transfer through a finite temperature difference.
That's all from us. Thank you.